Okay, so analogous to diffusing mass, as we saw with Fick's law, we can also consider this second case, which is the diffusion of heat, and that's known as Fourier's law. So imagine you have a hot plate and then a cold plate at a given distance. And then if I look at the temperature profile in the gas between these two plates, so let's look at T as a function of x, where x1 is the location of the hot plate, x2 the location of the cold plate. Then we're going to have a hot temperature at x1, cold temperature at x2, and typically to a good approximation you have a linear decrease in temperature. And so your gradient in T is actually a constant here. And Fourier's law tells us that the heat flux, which is typically written as Q, is negative K times the gradient of T. So if the gradient of T is constant, as in this case, meaning this is a straight line with a given slope, then our heat flux is also constant along this line from x1 to x2. And so in this case of Fourier's law, our units are a little different to Fick's law. Here K is the thermal conductivity of the gas between the plates. Q is the heat flux, and grad T is the temperature gradient. So let's look at the units. The unit of Q is typically given as watts per meter squared, which is joules per second meter squared. And the gradient of T is Kelvin per meter. And so if you combine these, you'll find that the units of the thermal conductivity, which is just Q divided by grad T, is watts per Kelvin per meter. So this is Fourier's law. Instead of mass or heat, there's one third example that we can diffuse, and that is the diffusion of momentum. And the diffusion of momentum is described typically by, so this is our third case, by Newton's law of viscous friction. And this law describes the diffusion of momentum between different layers of a fluid that have different velocities. And as a side note, here we have to be a little bit careful because momentum, MTM is my typical abbreviation for momentum, and velocity are vectors. So far we have looked at concentration fields and temperature fields, and those are scalars, and it's easy to formulate the diffusion laws for those scalars. But for a diffusion of momentum, you suddenly have vectors, and that makes the whole thing a little more complicated. So to just illustrate this, imagine you have a fluid flow that is faster near the top here, and then it slows down. So you have a velocity gradient, and this velocity here is u as a function of y and t, where y is the spatial dimension of our flow in the vertical, and on the horizontal here we have u. And so let's say this is u of y at time t1. And then what happens, let's zoom in to somewhere near the surface here. Let's zoom in and look at two layers of this fluid. So at the top layer that goes faster, and a layer beneath it that is slower. And these layers have viscous friction between them. And so as a result, the top layer will be slowed down, as it is shearing with the layer beneath, and the bottom layer is going to speed up. This is essentially like shear on a surface. So what happens over time is that our velocity u, the fast velocity near the top, is going to slow down, and the slower velocities near the bottom are going to speed up. So this is going to be our new velocity profile u as a function of y at time t2. And so this profile here has a vertical velocity gradient, duy. So that's a vertical gradient in horizontal velocity. So our way to describe this is that momentum from up here is transferred downward to the lower layers through this shear process. So horizontal momentum per unit mass diffuses downward, and the momentum flux corresponds to shear stress in a fluid. And the way we write Newton's law of viscous friction is that we say the shear stress tau is equal to the dynamic viscosity mu times the vertical gradient in horizontal velocity, du dy. And an important point to note here is that this is the incomplete version of the viscous friction law because it is a scalar form. Because in reality, you have three velocity components, not just u, but also v and w, and three surfaces. So not just the dimension y, but also x and z. And as a result, you have 9 components to your shear stress, and so you need a second order tensor. And we'll get back to that at a later stage. Now, one final thing to mention here is just the units of Newton's law of viscous friction. So the units of the shear stress is, as we said earlier, force per area, which is Newton per meter squared. And so as a result, the units of our dynamic viscosity mu are units of tau divided by the units of our velocity gradient du dy, which is Newton per meter squared times 1/1 per second. That's the unit of the velocity gradient. So we're left with kilogram meters per second squared times second per meter squared, which is kilograms per meter second. And later on in the class, we will define a different viscosity known as the kinematic viscosity. And the kinematic viscosity nu is defined as mu over density rho. So the units of mu are kilogram per meters per second times meter cubed over kilogram, which is meter squared per second. And so you'll realize that the difference between these two viscosities is that the kinematic viscosity has no mass involved. Yeah, it's just meter squared per second, whereas for the dynamic viscosity there's a mass involved. So that's why this is called the kinematic viscosity. And just for completeness, I want to mention here that this is the same units as those for mass diffusivity. And it makes sense that those have the same units because we can write the shear stress mu du dy in terms of a mass flux. Mu is just nu times rho, so we have nu rho du dy, which is nu times d by dy of rho u. So it is the kinematic viscosity times the gradient of the mass flux. Finally, du dy can be interpreted as the strain rate. And I've mentioned this before, the strain is the rate of deformation of the fluid, And so the difference in velocity between different layers tells you how quickly your fluid parcel is deforming. And we'll revisit this in a couple of lectures.